Hello, welcome to the course Two-Phase Flow and Heat Transfer. Today we are in 4th lecture. Today we will be discussing about drift flux model. So, let us first see what is the outline of this course. At the end of this lecture, we will understand the applicability of drift flux model in different adiabatic and phase change situations. We will be also deriving continuity and momentum equation applicable for drift flux model. Important terminologies involving drift flux model will be discussed in this lecture. We will also try to see for gas liquid vertical pipe flow what are the different operating points for upward and downward movements of gas and liquid. And at the end we will be seeing how critical heat flux can be calculated for departure from nucleate boiling. Now, to give you a brief idea about drift flux model, we will recap our last lecture homogeneous model. So, in homogeneous model we have seen that both gaseous phase and liquid phase are having same velocities, but here in drift flux model we consider that there is significant drop between the velocities. That means there is relative velocity between the gas phase and the liquid phase. Now, as it is having two different velocities, ideally we should consider two separate sets of equation. That means, in case of adiabatic flow, two continuity equations and two momentum equations, and whenever we are having heat transfer into consideration, we will be having two energy equations also. But in drift flux model, we are actually considering not only the individual phases, we are actually considering the relative motion. So, here what we consider, once again we give mixture kind of assumption over here for both the phases, and we are interested in gas relative velocity. So, altogether you will be finding out that we are having, in case of adiabatic situation, one mixture continuity, one mixture momentum equation, as well as we will be having gas relative velocity equation. So, if you consider both the phases separately, you will be having altogether 4 equations, 2 continuity and 2 momentum equations, but here in drift flux model, as we are only considering the relative velocity between the gas and liquid, we will be having 3 equations: the mixture momentum equation, mixture continuity equation and gas relative velocity equation. If heat transfer comes into picture, we will be having one mixture heat transfer equation also. So, let us see that drift flux model where it applies. Basically, we will be finding out drift flux model is applicable for bubbly flow, slug flow and droplet flow. So, wherever interface is not clearly distinct, just like your bubbly flow and droplet flow, and its immediate transition slug flow, we will be finding out drift flux model is applicable. Here already I have told that relative motion between the phases is considered. Now, these 3 equations already we have shown you in the first lecture. These are very important equations. So, you can find out JGF, this is the drift velocity. So, you can find out drift velocity is nothing but alpha into Ug minus J. So, this already we have shown you the definition. This is actually how gas velocity is drifting from the overall relative velocity. So, you can find out JGF is equals to alpha into Ug minus J. Then we have also shown you the proof of next 2 equations in the first lecture. JGF is equals to alpha into Jf plus of 1 minus alpha into Jg. This comes from the first equation once again. Here you are having alpha into Ug. If you try to write down Ug in terms of Jg, you will be finding out from this equation we are getting this one. On the other hand, if you start from this equation and try to reduce this J in terms of the individual phase velocities Ug and Uf, you will be finding out we are coming to this third equation. So, those things we have already shown you in the first lecture. In this lecture, we will be taking the clue from the first lecture, and these 3 equations we will be using. JGF equals to alpha into Ug minus J, JGF equals to minus of alpha into Jf plus of 1 minus alpha into Jg. By the way, this Jf and Jg, these are gas and liquid superficial velocities, and Jgf is equals to alpha into 1 minus alpha into Ugf, where Ugf is the relative velocity between the phases. Okay. Next, let us try to see a schematic of situation where drift flux model can be applicable. So, you see what I have shown you over here, this is a pipeline having variable cross section. So, you can find out this is smaller cross section compared to this one. So, you are having variable cross section, and then to show the relative velocity between the phases, we have considered both the phases are separate. So, you see at the bottom we have given liquid phase, and at the top we have given the gaseous phase. So, liquid phase is signifying F and gas phase is denoted by G. So, you can find out that as the flow is flowing from left to right, so we are having the mass of the liquid as rho f, u f and a f at the entry, and mass for the gas is rho g, u g and a g at the entry, right. On the exit side, you can find out rho f, u f and a f at z plus delta z, where we have considered delta z is actually the length of the pipeline. So, this is some sort of infinitesimal length we have considered. For finite length, we have to go for integration of this one, and on the other hand side for the gas u g, rho g, a g at z plus delta z. To make it generalized, we have considered that the pipeline is making angle theta with the horizontal direction. Apart from that, as we are having gravity in the downward direction, you will be finding out that we are having mass over here rho g alpha a into delta z for the liquid inside the pipeline, and inside the pipeline for gas, and rho f into 1 minus alpha a into delta z for the liquid in the downward side of the pipeline. Now, as we are considering the relative velocity between the phases, this interfacial force will be very important over here in drift flux model. You will be finding out that two interfacial forces we have given Fi for the liquid side and minus Fi for the gaseous side. Apart from that, if there is some sort of mass transfer, that means via phase change, if there is some sort of mass transfer, we have also given mass transfer gamma over here, which is actually occurring due to this interfacial area. So, this interfacial area is Ai, and then delta z is the length. So, you can find out that gamma into Ai into delta z will be the mass transfer. We have also considered in this model the wall friction force. So, you can find out the gaseous phase is actually finding out wall friction force Fwg. On the other hand, liquid side is getting Fwf. Okay. So, with this idea, let us now try to see how the continuity and momentum equation, mixture continuity and momentum equation can be constituted. Okay. Next, let us try to see the individual components first. So, here I have written the continuity equation for the liquid side. So, you can find out this is the unsteady part, which we have already seen in our fluid mechanics. So, this is the unsteady part del T of rho f into 1 minus alpha, and then we are having the inertia part 1 by a del z of a rho f into 1 minus alpha into uf. So, 1 minus alpha is coming into picture as we are considering the liquid part. Now, this minus gamma is actually due to the mass transfer. So, some liquid is converting into vapor due to phase change, we have considered over here to become generalized. So, that is why minus gamma we have added as the source term. On the other hand, in the gaseous phase momentum equation, it will be taking similar form of the liquid. So, in place of only 1 minus alpha, we have to consider alpha, because we know that alpha will be associated with the gaseous phase. So, this is first the unsteady part, and then we are having inertia part 1 by a del z of a rho g alpha into ug, and as gas has actually acquired mass due to phase change. So, we will be finding out gamma we have kept over here as positive. So, you see this is actually giving you the mass balance, because these two will be cancelling each other. Now, if we try to add these two equations, okay, if we try to add, then we will be finding out both these unsteady parts can be added. So, del T of rho f into 1 minus alpha plus of rho g into alpha, which is nothing but we know rho bar or average density. So, this also we have derived in case of your homogeneous flow equation, if you remember. So, there also we have shown that rho f into 1 minus alpha plus rho g into alpha will be rho bar. This also we have proved over there. So, we are considering after adding, we are having the unsteady part as del rho bar del T, right. On the other hand side, for the inertia part, you see we are having 1 by a del del z of, now here if we take a common, then it will be rho f into 1 minus alpha into uf plus rho g into alpha into ug. So, that is nothing but your g. Okay. So, here we can write down the mixture mass conservation equation as del rho bar del t plus 1 by a del del z of a g is equals to 0, because both the source terms will be cancelling from each other. Okay. So, this is the mixture continuity equation. Already I have shown you over here what is rho bar and g. Next, let us try to see the momentum conservation equation. In case of momentum conservation equation, you see first I have written for liquid as well as gas. So, liquid, let me explain the terms once again. So, first term is due to the unsteady behavior. So, del del t of rho f into 1 minus alpha into uf, and then we are having inertia term 1 by a del del z of a rho f into 1 minus alpha uf square. So, this is basically the inertia. We can also see from the figure that we are having some force over here, okay, gamma into ai into delta z. So, those components will be coming over here gamma into ui, where ui is the interfacial velocity. Okay. Then we are having the force due to pressure drop minus of 1 minus alpha into del p by del z. We are also having the frictional force in the negative direction. This is the force including the buoyancy. So, rho f into g 1 minus alpha into sin theta, because the pipe is making theta degree angle with the horizontal. And then we have included two terms, this is interfacial force Fi and then virtual mass force Fvm. Okay. So, this is the liquid momentum equation. Similarly, we can write down the gas momentum equation del del t of rho g alpha into ug. So, this first term is actually your unsteady term, and then we are having 1 by a del del z of a rho g alpha into ug square. So, this is the gaseous inertia. We are having minus of gamma into ui. You see here in liquid we have given plus of gamma into ui, here it will be minus of gamma into ui. So, due to mass transfer, whatever velocity we obtain, that is ui. So, this is coming as positive over here in liquid term and coming as negative in the gaseous term, right. On the other hand side, we are having the pressure drop, okay, and the wall friction force due to gaseous movement Fwg. Also, we are having the buoyancy component rho g alpha into sin theta, and rest two components the interfacial force and virtual mass force, but in the opposite sign as we have seen in case of the liquid. So, minus Fi plus Fvm. Now, once again, just like your continuity equation, we are going to add it over here. So, if we add, we will be finding out all these terms involving opposite signs in both these equations will be cancelling out. Only in the first term, you see del del t, if we take common, then we will be having rho g alpha ug plus rho f 1 minus alpha into uf. This is nothing but your g, which we have shown you in the previous slide. So, g is nothing but rho f into 1 minus alpha into uf plus rho g into alpha into ug. Okay. So, we will be writing down this term, unsteady term, as del g del t, right. Then in the second term, we are having 1 by a del del z of, here we are getting 1 by a del del z of a rho f 1 minus alpha uf square plus a rho g alpha into ug square. Now, here we need to do little bit of derivation. So, let us see how this term actually changes into the mixture momentum equation. So, we are having af rho f and then 1 minus alpha into uf square, okay, plus ag rho g alpha into ug square, right. So, this term what we can do over here, say rho f 1 minus alpha whole square uf square into af by rho f 1 minus alpha plus, on the other hand side you can find out we are having ag rho g square alpha square ug square divided by rho g into alpha, right. Now, you see over here we can write down this AF into 1 minus alpha into UF, this is nothing but your GF, okay, divided by rho F 1 minus alpha. Also we will be finding out, okay, one probably this F's will not be there. So, this is A, okay. So, A we can take common, okay, and here we will be having GG whole square by rho G into alpha, okay. Now, you see this GF can be written as G square into 1 minus x whole square by rho F 1 minus alpha, and here this one can be written as G square into x square from the definition of quality, mass quality rho G into alpha, okay, multiplied by A. So, you can find out, we can take A G square common and we can define this 1 minus x whole square divided by rho F into 1 minus alpha plus x square into rho G into alpha as a new term. So, what we have done over here, you see we have called rho dashed as 1 minus x whole square by rho F into 1 minus alpha plus x square divided by rho G into alpha to the power whole to the power 1 reciprocal of that as rho dashed. So, ultimately you will be getting A G square, which is this term, A G square, which is this term, and then divided by rho. That means if I consider this one as reciprocal of rho, so then you will be finding out A G square by rho dashed over here in our mixture momentum equation. So, these two term actually gives us 1 by A del Z of A into G square by rho dashed, right. Next, in the right hand side, let us see, in the right hand side if you see, you will be finding out here we are having del P del Z into 1 minus alpha, here we are having alpha into del P del Z, which will be cancelling out each other, and we will be finding out minus of del P by del T will be remaining, right. Similarly, here what we have done, the frictional force FWF for the liquid phase and FWG for the gaseous phase we have added up, and we have written FW overall frictional force in the mixture momentum equation. For the buoyancy force also same thing will happen as we have seen in case of the pressure force, rho F into rho G into 1 minus alpha into sine theta, and here rho G into G alpha into sine theta. If we add, then we will be finding out rho bar, where rho bar definition already I have shown you in the previous slide. Rho bar is rho F into 1 minus alpha plus rho G into alpha. So, we will be finding out that these two term if we add up, we will be getting rho bar into G into sine theta, right. So, this becomes my mixture momentum equation. So, we are talking about drift flux model. So, here the mixture continuity equation and mixture momentum equation will be coming into picture. Now, apart from that, as I have mentioned that we will be also considering the third equation, because the relative velocity comes into picture. Basically, we take in drift flux model the gas relative velocity. So, you see here the gas relative velocity is UGJ dashed, okay. So, which we call mean transport drift velocity, okay. Now, this mean transport drift velocity is actually given by Ishii as UGJ plus C naught minus 1 into J, this is actually area averaged of the J, right. Now, this mean transport drift velocity, which is very essential for the drift flux calculation, is dependent on two parameter, which one is UGJ and C naught, okay. What are these UGJ? Let us see over here. UGJ is actually gas drift velocity or local slip. So, how much the gaseous phase is actually slipping from the overall averaged velocity, okay. So, that is UJJ equals to this symbol, using this symbol whatever I have done, that is actually area averaged quantity. So, area averaged quantity of alpha into UG minus J divided by area averaged of alpha. So, this is the definition of UGJ. On the other hand, C naught, which is nothing but two phase distribution coefficient. So, that definition I can write down, C naught is equals to area average of alpha into J divided by area average of alpha and area average of J, right. So, once I know these quantities, that what is the area average alpha into J, what is area average of alpha, area average of J, area average quantity this one, we can find out what is C naught and UGJ. Once we get UGJ and C naught, we can put it over here to get the mean transport drift velocity. So, this mean transport drift velocity will be very important. This will be signifying that what is the relative velocity between the phases, specifically for the gaseous one. Now, there are several correlations for finding out this C naught and UGJ. Major correlation has been proposed by Ishii. So, here Ishii has given in 1977 that what is the value of C naught. He has given this empirical correlation 1.2 minus 0.2 root over of rho g by rho f, where rho g and rho f are the gaseous phase and liquid phase densities, into 1 minus e to the power minus 18 of area averaged of alpha or void fraction. Now, for UGJ we are having several correlations once again. Now, Ishii has given the flow regime based correlations. So, for bubbly flow he has mentioned UGJ is equals to root 2 of alpha into g into delta rho by rho f square, where delta rho is nothing but the rho f minus rho g to the power 1 by 4 into 1 minus area averaged alpha to the power 1.75. Similarly, for slug flow he has given this type of equation, right. So, using this type of equations you can find out C naught and UGJ, and you can put it over here to get the mean transport drift velocity. Okay. Now, let us try to see that how this drift flux model is helpful for finding out the configurations inside the pipeline. So, here we will take the help of two equations which I have derived in the first lecture. So, you can find out first equation which I will be using, JGF equals to alpha into 1 minus alpha into UGF. Okay. Now, if we talk about bubbly flow situation, that means lots of bubbles are there, we will be finding out that UGJ is actually a function of velocity of a free rising bubble. Okay. So, we can write down that UGF is actually U infinity into 1 minus alpha to the power B. Okay. So, you see here alpha is the void fraction, U alpha is the free rising bubble velocity, and B is actually a constant which varies in between 1 to 2. So, depending on the fluid parameters and the flow velocities, this B parameter actually varies, but its range will be in between 1 to 2. So, if I put this UGF in this equation, JGF equals to alpha into 1 minus alpha into UGF, we will be getting finally JGF equals to U infinity into alpha into 1 minus alpha to the power C, where C is nothing but B plus 1. Okay. So, that means the range of C will be in between 2 to 3, as B was in between 1 to 2. Now, this is very important equation. You see here, if I try to find out what is the value of JGF whenever alpha is 0 and 1, you will be getting that at alpha equals to 0 and 1, JGF goes to 0. So, obviously, the nature of the curve, if I try to plot in between JGF and alpha, this will be something like this, getting 0 at 0, getting 0 at 1, right. So, this is a typical curve between JGF and alpha if I consider that free rising bubble is there in stagnant liquid. Okay. Now, let us see the other extent. So, if we are having JGF equals to minus alpha into JF plus 1 minus alpha into JG, this equation also we have proved in the first lecture. So, you can find out from this lecture we are getting at alpha equals to 0, JGF becomes JG, and alpha equals to 1, if you put it over here, then you will be getting JGF equals to minus JF. Now, if I try to plot it over here once again in JGF and alpha plane. Now, remember these two things are not similar, because this is for free rising bubble, this is not for free rising bubble, this can be for any other configurations. So, here we get, you see, if alpha is 0, then we are getting JGF equals to JG. So, is in the positive side, let us say that this is the JG, okay, and whenever alpha equals to 1, JGF will become negative of the velocity magnitude for the liquid phase. So, negative side we have come, and then you see this is minus JF we have notified over here. So, if you try to join these two, then we will be getting this straight line for JGF and alpha equations. Now, these two curves are very helpful for finding out the operating point in case of the pipeline, whenever we are having bubbly flow or slug flow into consideration. Okay. So, let us try to see what happens. So, first I have shown you adiabatic vertical pipe. So, you see in case of adiabatic vertical pipe, I have here plotted JGF versus alpha. already this curve you know we have shown in the previous slide. So, it gets 0 over here at alpha equals to 0 and alpha equals to 1, right. Now, let us take several cases. So, first one we will be taking case A, which is both the phases are having downward flow. So, if both the phases are having downward flow, that means both Jg and Jf they are negative. So, if they are negative, then we will be finding out at alpha equals to 0, negative side we need to go for Jgf equals to Jg. So, that will be becoming minus Jg1, right. So, this is the operating point whenever alpha equals to 0. On the other hand, whenever we are going for alpha equals to 1, that is minus of Jf, and Jf is already negative. So, it will become in positive side. So, you will get the operating point somewhere in the positive side, let us say this one. So, if we join this line between these 2 points, so this will be my line whenever I have plotted between Jgf and alpha. Now, the operating point will be the intersection between the curve and the line whatever we have found out. So, this is my operating point OA. So, in this operating point at this alpha, the adiabatic vertical pipeline can stay. So, we can find out operating point is OA. Continuing like this, let us take the second case. We are having gas downward and liquid upward. So, if gas is downward, once again the at alpha equals to 0, the Jgf will become minus Jg. So, we have taken the same point for example, okay. So, this is my alpha equals to 0 point, and alpha equals to 1, that becomes minus Jf. Now, Jf liquid velocity is upward, so it will become positive, okay. So, positive multiplied by minus, so it will become negative. So, we will be having operating point at alpha equals to 1 somewhere in the downward side, let us say this point, okay. So, if we join between this point and this point, this is my operating line. Now, interestingly, you see the curve has never intersected this dotted line. So, that means in this case you will find out there is no operating point. So, you will get this type of flow, gas downward movement and liquid upward movement is never possible, okay. Next, let us see case C. So, in case C, both the phases we have taken upward. So, if both the phases are upward, so that means Jg and Jf both the phases upward. So, if Jg is upward, then I will be finding out at alpha equals to 0, we have to go in the upward side. So, let us take that point as this one Jg2, okay, in the upward side at alpha equals to 0, and as liquid is in the downward side, let us take the point somewhere over here, okay, with a negative liquid velocity, because negative into positive it becomes negative. So, this is the operating point for case C, right. So, if we join between these 2 points, then we will be getting our operating point is over here. So, this is the operating point for both the phases upward motion, okay. Now, continuing like this, if we go for gas upward and liquid downward. So, gas upward, liquid downward means obviously the gaseous points will remain over here and liquid downward point will be coming somewhere over here, okay, because liquid downward means negative velocity, negative it becomes positive. So, it comes somewhere over here. So, you can find out if we join these 2, we are getting 2 points as operating point OD1 and OD2. So, these 2 are actually called conjugate states or kinematic shock. So, it will be changing the position from one place to another place in these cases, right. Next, case E, gas upward and liquid downward, but a special case, let us say the liquid velocity is taking such a fashion that this line joining between Jg2 and Jfe2, we are getting such a fashion that this line is getting the tangent of this curve. So, this point we can call that starting from kinematic shock, it is converting into a single operating point. This is actually called a flooding limit. So, beyond this we will be having always flooding by some liquid phase, okay. Next, case F, high upward gas and downward liquid, both the velocities are very high. So, you can find out gas velocity, let us say somewhere over here, and liquid velocity is further up, you will be finding out there is no operating point between this curve and the line, okay. So, you will be finding out in this case we are having no operating point, and this actually is a typical example of flooding. Now, you see here the case E is a typical point where this line is actually the tangent of this curve. Now, if we take different gaseous velocities and liquid velocities and try to draw this operating point OE, okay, then we will be finding out that this curve whatever we have drawn from this from this JGF equals to U alpha into 1 minus alpha to the power c is actually the locus of all the flooding limits. Okay. So, you have to do the experiments for different liquid velocity and gas velocities, that means JGF equals to JF Jg at alpha equals to 0 and equals to minus Jf at alpha equals to 1, and we can find out this type of flooding limit points, and if we find out the locus of this flooding limit, that will be the curve, right. Next, let us try to see another important case, which is called pool boiling crisis. This is having heat transfer into consideration. So, let us try to find out the situation over here. So, in case of nucleate boiling, already we have learned heat transfer. So, we know that there will be a surface through which we will be applying the heat flux. So, as we are having the heat flux, so we can find out that lots of bubbles will be being generated over here, bubbles will be moving up and liquid will be coming down for replenishment, right. So, we are having two different situations over here, bubble velocity up and liquid velocity down. So, we have taken JV and JL into consideration. Now, this JV is signifying the vapor gaseous phase, we have written here as JG, and liquid phase JL we have written here as JF. Now, we know that Jg can be written as Q dashed by IFG, which is nothing but latent heat, into rho g. Similarly, Jf can be written as minus of Q dot IFG into rho f, because these two are not having similar magnitude on as well as direction. Okay, now we know already this equation. So, what we can do, we can put the value of Jf and Jg over here, we get a equation like this, Jfg equals to Q dot into Ifg into rho g 1 minus alpha into rho g by rho f. Now, if the density ratios are very high, so rho f is very higher compared to rho g, then I can neglect this term. So, I will be getting Jgf equals to Q dot by Ifg into Qg into 1 minus alpha, right. Already I know that for this type of bubble, free rising bubble, JGF equals to U alpha into 1 minus alpha to the power c, whereas c is nothing but in between 2 to 3. So, what we can do, we can equate this JGF and this JGF and we will be finding this equation. Now, to get the pool boiling crisis, what we need to do, we need to maximize the heat flux for a given alpha. So, del q dashed by del alpha equals to 0. Once you do del q dashed by del alpha of this equation, you will be getting optimum point alpha will be actually 1 by c from here, and using this we can have q dot c by Ifg into rho g is equals to u infinity into 1 by c into 1 minus 1 by c to the power c minus 1, which is equals to k into u infinity. Whereas this term is actually a constant, we can take this one as k, right. Now, if we try to find out the values of k, we will be finding out that for c equals to 2, because the c limit is between 2 to 3, for c equals to 2, k equals to 1 by 4, and for c equals to 3, k equals to 4 by 27. So, k will be varying in between 1 by 4 and 4 by 27. Then, to obtain the final value of the critical heat flux, let us balance the drag force and buoyancy. So, if you balance the drag force and buoyancy, so you will be getting, this is the drag force CD into pi by pi r square into rho f into alpha square by 2, and this is your buoyancy force 4 by 3 pi r cube is the volume multiplied by density ratio into g. So, you will be getting the terminal velocity u alpha in this fashion, where r is also there. Now, to obtain the r at which the bubble has released from the surface, we will be balancing surface tension and buoyancy. So, this is the surface tension force 2 pi r into sigma, and buoyancy force already we have discussed in the last one. So, here from you will be getting the departure radius of the bubble. Once we put this departure radius of the bubble over here, we will be getting u alpha, and if we put the value of u alpha over here in this critical heat flux term, we will be getting the final expression for the critical heat flux for departure from the nucleate boiling. So, here we have seen that using the drift flux model, how we can predict the critical heat flux for drift flux model. Okay, to summarize, what we have done, we have derived the continuity and momentum equation applicable for drift flux model, defined two-phase distribution coefficients and local slip for different flow regimes. We have also analyzed different operating points for gas liquid two-phase flow, and finally, we have shown you the critical heat flux for departure from nucleate boiling. Let us have some practice. So, we are having 3 questions over here. So, drift flux model considers local slip between the phases. So, your answer in between true and false. obviously the correct answer will be true always. Next, at alpha equals to 0, drift flux will be JGF will be 4 options we are having minus JG, JG, JF and minus JF. The answer is JG. Then for gas upward and liquid downward flow in a pipe, we are having 4 options: no operating point exists, 2 operating point exist, 1 operating point exist and flooding can happen. So, which is the correct option? So, both these things can happen. 2 operating point can exist for a particular velocities and flooding can happen at higher liquid velocities. So, with this I will be ending this lecture. Thank you.